So apart from the properties of the ferromagnetic material, we had discussed yesterday the hysteresis loop. The why at all we get a hysteresis loop, or what we mean by a hysteresis loop. So it is defined as the lag in the changes of magnetization while we change the magnetic field. Now, because of hysteresis, as I have said already, that the magnetization of ferromagnetic material depends not only on the strength of the magnetic field that you have over here at a given instant, but also on the magnetization history of the material. Okay, so we have observed that if an initially unmagnetized specimen of a ferromagnetic material is subjected to increasing or decreasing magnetic fields. So suppose it's subjected to increasing magnetic field, or it is subjected to decreasing magnetic field. Okay, then the magnetic field induction B varies as a function of H along a closed loop like this, which is the hysteresis loop. Now the curve over here, it begins at the origin O. So this is the origin O, and as H is increased, as you increase H, the field B begins to increase slowly, and then it increases quite rapidly. First it increases slowly and then it increases quite rapidly until it comes to saturation. So this is the saturation value for the magnetic field, which is Bs. And then when we try to decrease the field, instead of tracing the original path, it takes a new path in such a manner that now when the field is zero, the magnetic field is no longer zero. So this is called remnant flux density, or remanescence. Remnant flux density or remanescence. REMANENCE. It is called magnetic flux density or remanence. So this is how it looks like, you see. Magnetic flux density or remanence here. So that happens when we now decrease the magnetic field intensity. That means it doesn't follow the original path. Okay, so now the specific property that we observe at this point, what we had studied yesterday, is the following: that the magnetic field therefore remains magnetized even in the absence of an external magnetic field. This is what we try to say over here, that the magnetic field, in the absence of an external magnetic field, the magnetic field remains. So there is a sort of a memory, it retains its magnetism. Now, to reduce the magnetic induction while the specimen, if you want to reduce this to zero, suppose say, if you want to reduce this magnetic induction to zero, how do we do it? This happens over here. That means we have to apply a negative field of minus Hc. Okay, if we do that, only then this comes down to zero. Okay, it is externally applied in a direction opposite to that of the original field. So it is called coercivity or coercive. It is called coercivity or coercive force. Okay, now as the applied field is increased in negative direction, saturation is ultimately reached in this direction again, and then the whole thing follows the same trend as it had followed originally, yielding again a negative remanence, which is minus Br. Here that was plus Br, so this is minus Br. Okay, and a positive coercivity, which you see this is plus Hc. This one was minus Hc, So this is actually plus Hc. So this is a positive coercivity. So this entire BH curve is known as the hysteresis loop. Now we had also discussed about the origin of magnetization yesterday. So origin of magnetization comes from, if we talk about the origin of magnetization, all right, let us talk about the origin of magnetization. Okay, so origin of magnetization. Okay, so what are the origin of magnetization? Well, we have observed, we have discussed. One is the orbital motion of the electron, isn't it? Okay, now just for the sake of recapitulation, all right, for the sake of recapitulation, let us recapitulate. An electron, for an electron moving in an orbit round the positively charged nucleus, okay, the angular momentum L is given by m v r, where v is the linear velocity, r is the radius, this is r, and m is the mass of the electron. This is what L is the angular momentum. It is given by this. Now what was Bohr's theory? What did Bohr say? That angular momentum is an integral multiple of h cross. This comes from Bohr's theory. This comes from Bohr's, it comes from Bohr's theory. Okay, that angular momentum is an integral multiple of h cross. All right, now, well, we have I have also told you from the present chapter that the magnetic field set up by the orbital electron is quite similar to the field around a bar magnet and is characterized by a magnetic dipole moment, isn't it? The magnetic field which is set up by the orbital electron is similar to the field around a bar magnet, and it is characterized by magnetic dipole moment. So it is like finding the magnetic moment of a current loop. So the magnetic moment, okay, of a current loop, the magnetic moment of a current loop is similar to the magnetic field set up, magnetic field due to an orbital, due to an electron orbiting around the positively charged nucleus, isn't it? The magnetic moment of a current loop is similar to the orbiting electron around the positively charged nucleus, isn't it? Okay, so, well, mu is equal to I times A. Mu is equal to I times A. Now what is I? It is Q by T or E by T, so to say, isn't it? And what is A? A is the area, so it is pi r square, isn't it? R is the radius of the orbit and T is the time period. We say that T is the time period. Okay, all right. So now what is V? The velocity. How do we define velocity? It is circumference 2 pi r divided by t. Under this situation, V, the linear velocity, can be written as 2 pi r. We can write it as 2 pi r divided by t, isn't it? Okay, so that is V. So, well, then mu m, if we call this mu m, magnetic moment, mu m will be equal to E pi r square, and for one, instead of 1 by t, we write V by 2 pi r. E pi r square into V by 2 pi r. We can write it in this manner. Okay, so what is this equal to? You see, r will cancel, pi will cancel. What do we get? We will get, yes, what will we get over here? E V r by, isn't it? This is what we'll be getting. You see, we'll be getting E V r by 2. Okay, this is what we'll be getting over here. All right, now you see, so that is EVR by 2. So now we can say that, what can we say now? See, we can say that mu m is equal to what? It is equal to E V r by 2, isn't it? So what is so how do we write it in terms of angular momentum L? L, we have already said, what is L equal to? L is equal to NH cross, or L is equal to MVR, isn't it? NH cross, or okay, so we already have L is equal to NH cross, and this is also equal to MVR, isn't it? So VR we can write as L by M, isn't it? So we can write this as mu m is equal to E by twice M L, isn't it? We can write it in this manner. This can be written following this. We can write this. All right, and again we can write for L, we can write this as E by twice M, okay, N H cross. We can write it E by twice M, N H cross. Can we write it or we can't? We can. Following the previous line, we can write this as equal to NH cross. Now this E by twice M, this E by twice M, we write as mu B. Okay, so this we write as E by twice M H cross. Okay, this we write as, well, mu B N. Okay, all right. So basically, therefore, what do we get for the magnetic moment of the atom? For the magnetic moment of the atom, therefore, we get, we write it as, for this N, we write it as this is equal to basically we don't call this as N, we call this as M. So this is the because of the magnetic nature of the electron, we call it because of the magnetic moment, we call this as M, which is a function of L, the orbital angular momentum. So this is actually equal to ml h cross, mu b into ml. Okay, so here we found the value of mu b as, all of you found it yesterday, it was 9.274 into 10 to the power minus 24 ampere meter square, isn't it? And this is called, what do we call this? This is called, yes, what is it called, this mu b? It is your Bohr magneton. All right, so this occurs from the orbital angular motion of the electron. Okay, the Bohr magneton is the elementary electron magnetic moment. It is elementary in the sense that no electron can have a magnetic moment below mu b. Mu b is the minimum. It represents the minimum non-zero value of the projection of the magnetic moment of the electron in an arbitrary direction. That means when ml is equal to 1. Okay, all right. Now the spin angular momentum, if we consider, it is mu m, but not orbital, it is spin. Here it was mu m orb. Here it was, like we were talking of mu m, here it was, see, mu m orb, that means orbital, but here it is mu m spin. Okay, so when that occurs because of the spinning of the electron around its own orbit, not around the nucleus, but right just around its own orbit. So this is equal to minus E by m, the spin quantum number Sz. Now this Sz, as you know, takes the value plus minus half. Okay, h cross. It takes the value plus minus half h cross. So mu m spin is equal to E h cross by twice m. Okay, so this is equal to plus minus mu b. It is just equal to plus minus mu b. So each orbital in an atom accommodates two electrons which orient themselves in opposite directions and revolve in opposite direction. Okay, so because of this, the spin and orbital magnetic moments of the pair cancel each other. So consequently, an atom having completely filled electron subshells or shells does not possess permanent magnetic moment. Hence, magnetic moment of an atom is determined only by the electrons which occupy partially filled shells. So, if they cancel one another, suppose if you have equal number of electrons, okay, then if they cancel one another, you won't have a net magnetic moment. So, only for partially filled shells, you get a net magnetic moment. So, in majority of the cases, the partially filled shells happen to be the outer valence shells. The electron spins, and orbital magnetic moments in the outer shell tend to orient themselves in opposite directions so as to compensate each other to the maximum possible extent. They try to compensate so that there is no net magnetic moment. So the magnetic moment of a free atom is mainly determined by uncompensated spins of the other electrons. So that's what I told you all in the beginning of the class, the meaning of uncompensated spins. Okay.